Dear students, welcome to SAIMEDHA Koti, Hyderabad. Today I am going to discuss an important topic in digital communication known as matched filter. What is the topic of the discussion? Matched filter. Let me put the heading. Matched filter. See, if you observe any competitive exam, a question from matched filter is compulsory, and the students feel difficulty with this topic called matched filter, but I am very much confident that after listening the lecture you will fall in love with matched filter. Now Violet, let's start matched filter, and we'll start from very basic. First of all, how you are going to start? Here what I said, what is the purpose of match, or before going to see the purpose, where matched filter is used. Matched filter is used in the receiver of digital communication. Where it is used? Matched filter is used in the receiver of what? Digital communication system. Digital communication system. Why it is used? Let us observe. Now, for knowing the purpose of matched filter, we'll start like this. See, we know that in digital communication, information is transmitted in the form of ones and zeros, right? So, let me write that point. In digital communication, how information is transmitted? Information is transmitted in the form of ones and zeros. Okay. Now, how we are going to transmit these ones and zeros? We are going to represent these ones and zeros in various electrical formats. Suppose I take a popular scheme known as on-off signaling. On-off signaling. See, in that scheme what happens, if we want to transmit binary 1, we will transmit a rectangular pulse like this of width TB. If I want to transmit binary 1, I will transmit a rectangular pulse of width TB and some voltage plus 5 volts. So this is my S of t. If I want to transmit the binary 0, I will transmit nothing. So in the interval 0 to TB, we transmit nothing. Right? See, this scheme I am going to use for explaining the concept of matched filter. Right? Now, assume that you transmitted either 1 or 0. Either 1 or 0 you transmitted, and I am going to consider baseband data transmission. Baseband data transmission means information is transmitted through fiber optic cable. Now, after this 1 or 0 is reached at the receiver, now how the receiver is going to make a decision that whether a 1 is transmitted or 0 is transmitted. Now the receiver will follow a process like this. To the received information, the receiver will sample the received pulse at a particular instant. The receiver will sample the received pulse at a particular instant, and it will compare based on the threshold value, in a threshold comparator. Suppose if the input value after sampling is greater than the threshold value, then the decision is taken in the favor of 1. Okay, 1 is transmitted. If the sampled value is less than the threshold value, then output is taken or decision is taken in the favor of 0. Right? Now what is input to the sampler? Either 1 or 0. And how we are going to transmit 1 or 0? In the form of rectangular pulses, and I told you that we are going to use on off signaling, right? Say I transmitted 1, binary 1 I transmitted, means what is the input to the sampler? The input to the sampler is a rectangular pulse like this. The input to the sampler will be a rectangular pulse like this. This is 5 volts, isn't it? Yes. Now, whenever this pulse travels through the channel, in the channel there is a possibility of noise occurring. Definitely there is a possibility of noise occurring. Noise is unwanted. So what I am going to do is, the noise signal I am going to represent with red color. Noise signal I am going to represent with red color like this. So what is input to the sampler? What is input to this sampler? Sampler is nothing but switch operation, so I represented like this. What is input to sampler? Signal plus noise. Signal plus noise is input to the sampler. Right. Now what I said, this sampler will sample the received pulse at a particular instant, and it will take the decision based on the threshold value. And what is the threshold value? Remember, when ones and zeros are transmitted with equal probability, ones and zeros are transmitted with equal probability, the threshold value is Vmax plus Vmin by 2. Vmax plus Vmin by 2. Now maximum value is 5 volts, minimum value is 0. So Vmax plus Vmin by 2 means here in our particular case it becomes 2.5 volts. 2.5 volts. Right. Now assume that, dear students, assume that here I am going to sample at T1. Assume that I am going to sample at T1. See, at T1, if you observe, noise is present, no? Noise is present. If noise is absent, if I sample at T1, what is the value I am going to get? 5 volts. But as noise is present, assume that the value what you are going to get is 4.8 volts instead of 5 volts. 4.8 volts instead of 5 volts. Now, what is the sample value? 4.8 volts. What is sample value? 4.8 volts. What is the threshold value? 2.5 volts. 2.5 volts. So 4.8 volts is greater than 2.5 volts. Yes, decision is taken in the favor of 1. Right? So 1 is, we can come to a conclusion that, oh, 1 is transmitted. So no errors. No errors. Why no errors? Here at T1 you can observe that signal to noise ratio, signal power by noise power is less. Signal to noise ratio is less. So our decision is correct. Suppose instead of T1, if I sample at this instant, now say at this instant the voltage is, the noise is coming in the opposite direction now. So assume that this is 1.8 volts. 1.8 volts. So if I sample at T2, what will happen? Here the input to the threshold comparator, here TC is threshold comparator, sampled value is 1.8 volts. 1.8 volts. So threshold value is 2.5 volts. Right? So 1.8 volts is less than 2.5 volts. What will happen? So decision is taken in the favor of 0. Decision is taken in the favor of 0. But what is transmitted? 1 is transmitted. Why we are going to get error when you are going to sample at an instant T2? Because at the instant T2 signal to noise ratio is less. Signal to noise ratio is less. Now if signal to noise ratio is less here, what is going to happen? The probability of error is going to increase. What is going to increase? The probability of error is going to increase. Now we must have a remedy for this problem. I think you understood the problem. See, the problem is coming due to this noise. If the signal to noise ratio is more, no problem. But If the signal to noise ratio is less, as we are having at instant t2, yes, probability of error is increasing. Now what is the remedy? What is the remedy? I think you understood the problem. Now we must search for the remedy. What is the remedy? Now the remedy I will tell you like this. What if I have a block? What if I have a block before the sampler? What if I have a block before the sampler which increases the signal to noise ratio, of the received pulse, and what happens if it also tells us, that block also tells us the point where we have to sample? We are at advantage, no? What I am saying? See, if we have a block before this sampler which increases the signal to noise ratio of the received pulse, and if it also tells us an instant where to sample so that we won't get any errors, will at an advantage, no? Will be at an advantage. Yes, that block is nothing but matched filter. So we can draw the matched filter like this. Now here in the receiver we will be getting signal as well as noise is also added. Right, here before the sampler I am going to include the block called matched filter. It is an LTI system with impulse response h of t, and the output of the matched filter is sampled. And what is the purpose of this matched filter? It must increase the signal to noise ratio of the received pulse. Simple. And it will also tells us the instant where we have to sample. Okay. Now this is sampling is done some at TB. Right? This is S0 of t I am assuming. So sampling is done means S0 of TB. And signal to noise ratio must be maximum. At the output of the matched filter, and this sampled value, yes, is given to what? Threshold comparator supplied with a threshold voltage VTH. From this here output is taken. Right? And we are showing the matched filter. Our hero is here. Matched filter. Now what is aim? What is our aim in this matched filter? Remember that matched filter has to maximize the signal to noise ratio of the received pulse, and in the process of maximizing the signal to noise ratio, we have to find out the impulse response of matched filter. That is our aim. We have to find out the impulse response of matched filter which maximizes the signal to noise ratio. So let us find out the signal to noise ratio at the output of the matched filter. So let me put the subheading. Now what we are going to calculate? Signal to noise ratio, signal power by noise power at the output of the matched filter. Right. So we'll do one thing. We'll find out the signal power and we'll find out the noise power separately, and then we'll divide. Right. The first one is signal power. In any competitive exam, the concept of matched filter is compulsory and the question is guaranteed. Right. Now signal power. Now assume that here input to the matched filter is signal. And here for this system that is called matched filter, which is a LTI system, input is there, impulse response is there. Can you calculate the output? Yes. We know that given input and impulse response, output of LTI system is nothing but the convolution of input with impulse response. Convolution of input with impulse response. And applying Fourier transform, we know that convolution in time domain is equivalent to multiplication in frequency domain. Convolution in time domain is equivalent to multiplication frequency domain. Now from this again, if I try to calculate the inverse Fourier transform S naught of t, the expression for inverse Fourier transform would be integral minus infinite to infinite S naught of f into e power minus j 2 pi of t df. Now what is S naught of f? S of f multiplied with h of f, no? So I can write like this: S naught of t is equal to integral minus infinite to infinite S naught of f, S of f, h of f into e power j 2 pi of t df. Right? Now this S naught of t is sampled at tb, no? So S naught of tb, if I write here S naught of tb, what will happen? In the place of t, simply substitute tb. So this becomes integral minus infinite to infinite S of f into h of f into e power j 2 pi of tb df. Right? Now after sampling this S naught of tb is a value, DC value. So DC, suppose if you have a DC signal, power means what? DC square. So here I can write signal power. If I denote it by capital S, is nothing but magnitude of S naught of tb whole square. Means capital S is equal to magnitude of integral minus infinite to infinite S of f into h of f into e power j 2 pi f tb df whole square. Right? Again I can simplify this as, small simplification I am doing, integral minus infinite to infinite h of f into S of f into e power j 2 pi f tb df whole square. Right? Signal power anyway we calculated. Okay, signal power we calculated. Let us find out the noise power. Okay, so let me put the subheading noise power. Noise power. For calculating the noise power, assume that additive white Gaussian noise is present at the input of the matched filter. So considering additive white Gaussian noise at the input of the matched filter, now it can be shown like this. This is my matched filter with impulse response h of t. Additive white Gaussian noise means it has got constant power spectral density. So input power spectral density is PSDI, and the output power spectral density I can denote it by PSDO. And we know the relationship between input power spectral density and output power spectral density, that output power spectral density is equal to input power spectral density into magnitude of h of f whole square, isn't it? Or output power spectral density is equal to input power spectral density is n0 by 2. So white noise means it will have constant power spectral density n0 by 2 into magnitude of h of f whole square. And from the power spectral density, how we are going to calculate the power? output power N naught is equal to area means integration. Output power is equal to area under the power spectral density, or N naught is equal to, what will happen, this is constant, N naught by 2 is constant. So, integral minus infinite to infinite magnitude of h of f whole square df. So, this is output power, and I got output noise power I got. Let me write output noise power, and signal power also I got, no, signal power. So, let us find out the signal to noise ratio. So, here I will have a separation like this. Yeah, signal to noise ratio is nothing but, what is signal power I got? Yes, magnitude of integral minus infinite to infinite h of f into s of f into e power j 2 pi f tb df whole square by noise power. Noise power is N naught by 2 integral minus infinite to infinite magnitude of h of f whole square df. Right. Now, we have to simplify the numerator term. In order to simplify the numerator term, we are going to use an inequality known as Squart's inequality. Squart's inequality, which says that suppose if you have this kind of expression, magnitude of integral minus infinite to infinite f1 of t into f2 of t dt magnitude whole square. Suppose if you have this kind of expression, so this will be less than or equal to integral minus infinite to infinite magnitude of f1 of t whole square dt multiplied with integral minus infinite to infinite magnitude of f2 of t whole square dt, right? And we'll call this as LHS and we'll call this as RHS. And remember that this LHS is equal to RHS. LHS is equal to RHS if f1 of t is equal to f2 star of t. f1 of t is equal to f2 star of t. Now, here what we will assume is, we will consider this to be our f1 of t and this term to be our f2 of t, right? Now, what can you write? I can write like this now. So, signal to noise ratio is less than or equal to, if you try to simplify this expression using Squart's inequality, what happens? So, integral minus infinite to infinite magnitude of h of f whole square df multiplied with integral minus infinite to infinite magnitude of this one, magnitude of e power j 2 pi f t b will be 1, no? So, what you will get here? Magnitude of s of f whole square df by this one. So, what is that you are going to get? Integral minus infinite to infinite magnitude of h of f whole square df multiplied with integral minus infinite to infinite magnitude of s of f whole square df by n naught by 2 integral minus infinite to infinite magnitude of h of f whole square df. Right? Now, here this term they get cancelled, yes or no? R s by n is less than or equal to 2 times of integral minus infinite infinite magnitude of S of f whole square df by n naught by n naught. Now we have to simplify this integral. If you remember your topic called signals and systems, you might have studied a relation known as Parseval's relation or Rayleigh's energy theorem. Parseval's relation or Rayleigh's energy theorem, which says that if the signal S of t forms a Fourier transform pair with S of f, capital S of f, and if you want to find out the energy in the signal, that is this one, energy in the signal S of t, you can use your Fourier transform, that is energy in time domain is equal to energy in frequency domain, S of f whole square df, means here simply I can replace this integral, here I can replace this integral with energy, I can replace this integral with energy E, because this is nothing but energy in the received pulse S of t, right? Or how can you write, if I separate these two, observe here, how can I write? I can write this expression as signal power by noise power is less than or equal to, this is 2E by n naught, 2E by n naught. Okay, now if signal to noise ratio is less than or equal to 2E by n naught, what is the maximum signal to noise ratio? Maximum signal to noise ratio is 2E by n naught, where E is energy in S of t, where E is energy in S of t. Here is equal to I kept, no? So is equal to I kept means what? This LHS in the squads inequality, what we discussed, the LHS is equal to RHS when F1 of t is equal to F2 star of t. So F1 of t is equal to F2 star of t means F1 of t is this one, F2 star of t, let us find out. Or this will happen if H of f is equal to S star of f, F1 of t is equal to F2 star of t, e power minus j 2 pi of tb. Alright. Now we have to find out the impulse response. So how to find out the impulse response? By calculating the inverse Fourier transform. How to find out the inverse Fourier transform? See, for getting the inverse Fourier transform of this expression, I want to tell you some basics, that if you can recollect your properties of Fourier transform, shifting property and conjugation property, your life will become very easy. So what does the shifting property say? Shifting property says that if x of t forms a Fourier transform pair with x of f, then x of t minus t naught forms a Fourier transform pair with e power minus j 2 pi f t naught into x of f. Or inverse Fourier transform of e power j 2 pi f t naught into x of f is x of t minus t naught, x of t minus t naught, alright. And observe here, or you can understand in other way also. How? If you want to get, look here, if you want to get the inverse of e power minus j 2 pi f t naught into x of f, what I am saying is, to this x of f, first get the inverse. X of f inverse is x of t. In this x of t, wherever you have t, replace it with t minus t naught. In this x of t, wherever you have t, replace it with t minus t naught. Can I say that? Yes. If you want to get the inverse of e power minus j 2 pi f t naught into x of f, or get the inverse of x of t, in this x of t, wherever you have t, replace with t minus t naught. right? And one more property you have to recollect, that is conjugation property, which says that if the signal x of t forms a Fourier transform pair with x of f, then x star of t forms a Fourier transform pair with x star of minus f. What happens if I take the reversal? Reversal in time domain has the equivalent effect of reverse in frequency domain. Reversal in time domain is equivalent to reversal in frequency domain. Right. Now what is our h of f? Observe here. Our h of f is s star of t multiplied with e power minus j2 pi of tb. Right? Or observe here. S star of f, no, not t here. Let me verify. S star of f. Or how I can write? E power minus j2 pi of tb multiplied with s star of f. Right. Now we must get the inverse Fourier transform for this one. So how to get? Observe here. Again I am writing here. So e power minus j2 pi f tb into s star of f. What I said? First of all, get the inverse of this s star of f. S star of f. Look here, x star of f inverse is x star of minus t. So inverse of s star of f would be s star of minus t. In this, wherever you have t, replace it with t minus t naught. But in the place of t naught, I have tb. So s star of t minus tb. Or the impulse response h of t. This is h of f, frequency response. Impulse response I got. Impulse response is s star of tb minus t. Yes. So we got the impulse response of the matched filter, and impulse response of matched filter is related to the input s of t as h of t is equal to s star of tb minus t. So to give a small recap, I can say like this. Matched filter is used to increase the signal to noise ratio, increase the signal to noise ratio of the received pulse in the receiver of digital communication, right? And what is the maximum signal to noise ratio at the output of the matched filter? 2E by N naught. 2E by N naught, where E is the energy in the received pulse S of t, and in the process of maximizing the signal to noise ratio, what is the impulse response of matched filter? Impulse response of matched filter is h of t is equal to s star of tb minus t. Or I can say that the impulse response of matched filter is related to the input s of t in this way. Hope you understood this one. For example, now if the received pulse is like this, this is the received pulse, s of t. This is the received pulse. Now if this is the received pulse, definitely this kind of questions are expected. What is the impulse response of matched filter? Just now we have seen how to find out the impulse response of matched filter, s star of tb minus t, right? This is s of t. From this s of t we must go to s star of tb minus t. How we are going to reach? See, this s of t being real, I can simplify like this: s of tb minus t. Do you have any objection? No objection. Again, this can be written as s of minus t plus tb. Yes or no? So from s of t I must go to s of minus t plus tb. See, in signals and systems you might have studied many different techniques. How to get this S of minus t plus tb from S of t. You can go with first shift then scale, or you can go with first scale then shift. Okay, many methods you might have studied. First scale then shift if I perform here. So look here, this can be written as S of minus of t minus tb. So S of t is there with us. From this S of t, here minus is there, take reversal, and here also minus is there. So to that reversal, delay by tb, delay by tb. So this is my S of t. Reversal if I take, okay. Now if I delay this by tb, delay means right shift. Yes, this is the impulse response. Now if you observe, the input and impulse response, are the same, hence the name matched filter, but in all the cases, input and impulse response will not be the same. In this case, input and impulse response are same. So this is the impulse response. And we know that if you know the input and impulse response, yes, we can find out the output using convolution. Now perform the convolution for these two. And convolution of two rectangular pulses of equal widths, triangular pulse like this. So this is 0. And in convolution, output ranges from sum of lower limits to sum of upper limits. You see how many concepts are going to come in one discussion called matched filter. Signals, communication, how many concepts are going to come. So this one. Here this will be a square tb. So this is my S naught of t. Which is input to the sampler. Now if I give this kind of pulse to the sampler, if you observe, this is the received one. Now this is input to the sampler. You can observe signal to noise ratio is increased. Right. See, if noise occurs also, yes, signal to noise ratio will increase, but at what instant the sampler has to sample? I can say that the sampler has to sample at this instant called tb. The sampler has to sample at an instant called tb, because at tb the value is maximum. So I can write an important point that the sampler at the output of the matched filter, the sampler at the output of the matched filter must sample at tb, because the value is maximum at tb. Right? And we have seen now one more purpose of matched filter is it has to increase the signal to noise ratio, and it must tell us at what point we have to sample. So at tb we have to sample. Right? Now if you observe, the sampled value at tb is nothing but a square tb, which is energy in the input signal. See, if you are having this kind of rectangular pulse, what is the energy? Energy is nothing but amplitude square multiplied with the width, right? So we can add one more important point, that the sample value is equal to the energy of input signal, and the maximum value, that is this energy of the input signal, and the maximum value occurs at a point, means at TB it has occurred now, which is equal to the duration of the input signal, occurs at a point which is equal to the duration of the input signal. Right? So in this way we are going to understand this beautiful concept called matched filter. If anybody asks you what is the purpose of matched filter, means you must reply, matched filter has to maximize the signal to noise ratio of the received pulse. And what is our objective in matched filter? Our objective is, in the process of maximizing the signal to noise ratio, we have to find out the impulse response of the matched filter, and the impulse response of the matched filter is related to the input S of t like this. Right? Hope you understood this concept. For more details, contact SAIMEDHA, Koti, Hyderabad. Thank you.